Hello and welcome to the video on Bernoulli's equation. Let me start with a case study. On the night of May 31, 2009, Air France Flight 447 took off from Rio de Janeiro in Brazil. Its destination was Paris. While it was flying over the Atlantic Ocean, it encountered a region of severe thunderstorms. The pitot tubes, which measure the airspeed, became jammed by ice. This led to autopilot disengagement. The pilots misinterpreted the airspeed data from the faulty pitot tubes and the aircraft stalled. Finally, the aircraft crashed, killing 228 people on board. The pitot tubes work using the principle of Bernoulli's equation. In this video, we'll learn about the Bernoulli's equation and the principle behind the pitot tubes. The Bernoulli's equation is given by the equation 1 in the slide. It states that the pressure energy plus the kinetic energy plus the gravitation potential energy is a constant. The Bernoulli's equation is basically the law of conservation of energy. You can see from the equation that the Bernoulli's equation describes the relationship between the pressure and the velocity. Now, it's important that the Bernoulli's equation is not applicable everywhere. The Bernoulli's equation is applicable for a flow along a streamline. Now, a streamline is a curve which is tangent to the velocity at every point. The two streamlines are shown in the figure on the right. In the first figure, the fluid is traveling through a straight pipe, and in the second figure, the fluid is flowing through a vertical wall. Second, the flow should be incompressible. That is, the density of the flow should be a constant. Third, the flow should be steady. That is, the pressure and the velocity should not vary with time. They can vary with position, but not with time. And lastly, the flow should be inviscid. The viscosity should be zero. That is, the fluid should be an ideal fluid. Now, we will derive the Bernoulli's equation using the Navier-Stokes equations. The Navier-Stokes equations are the law of conservation of momentum. On the left hand side is the acceleration, and the Navier-Stokes equation states that the acceleration is equal to the pressure gradient plus the body force plus the viscous forces. Now, can you apply the four assumptions of the Bernoulli's equation and obtain equation 5? When you integrate the equation 5, you get the Bernoulli's equation. Now, we'll see an example of where the Bernoulli's equation can be applied in practical life. The figure shows a flow over a flat plate. The blue region is dominated by viscous effect due to its proximity to the wall. So the Bernoulli's equation cannot be applied on the blue region. It can only be applied on the white region. Now we'll talk about the pitot-tube. The pitot-tube measures the airspeed. In the figure on the left, there is a pitot-tube which measures the flow through a pipe. So, fluid is flowing through a straight pipe. At point 1, there is a static port, and at point 3, there is a pitot-tube attached. The points 1 and 3 are along a stream line. So, we can apply Bernoulli's theorem along point 1 and 3. Applying at point 3, the velocity is 0 because the pitot-tube has very narrow cross section at point 3. So, applying Bernoulli's theorem and putting V3 as 0, we can obtain the velocity at point 1 in terms of the pressure at point 1 and 3. Now, pressure at point 1 and 3 can be given in terms of small h and capital H as shown in the figure. Thus, we can obtain the velocity of the fluid. Now, another application of Bernoulli's theorem is a Venturi meter. The figure shows a Venturi meter which has a converging section, then a throat which has a constant cross section, and then a diverging section. As the section converges, the area decreases, and due to continuity theorem, as the area decreases, the velocity will increase. And since the velocity will increase, the pressure will decrease. The pressure will be lowest at the throat. And as the area increases, the pressure will again increase. That's the Venturi meter. And since you know the pressure at various points, you can calculate velocity in terms of the pressure again, similar to the pitot tubes. So that's it for the lecture. Thank you.